I'm pleased to introduce our next feature session, Storage is Software, Optimize It. And this session is moderated by Dan Finn Foley. Dan?
Thank you so much, and welcome to our featured session, Storage is Software. I love the titles that our friends at ESA come up with for this. This one sounds a little dangerously close to Bitcoin as a battery, but in this case, I think it's really quite true, and we'll get into that in our panel discussion today. Storage is one of the incredibly critical flexible assets, and storage is the element that gives it that flexibility. So really looking forward to diving into this discussion. Before we do that, a few housekeeping items. We have a limited time for the discussion. Obviously, we could spend 2 or 3 days talking about software, but we'd love to make it as impactful as possible. So please put your questions into the Q&A panel in Zoom, where you'll find that, and we'll try to get to as many of those as we can throughout the discussion. That really makes my job very easy when the audience provides the questions that are most impactful for them. Instead of a traditional sort of Q&A at the end of the session, we'll be following ESA to an open forum discussion on the topic in the lounge, where you can ask questions, give your thoughts and opinions on the topic, and hear from the industry leaders again. One last note, the session will be available on demand beginning April 29th at the ESA Conference 2021 website. So without further ado, I'd love to do a quick introduction. I'm thrilled to be joined by Dr. Colleen Leakin, lead data scientist for Fluence, and Nate Diamond, manager software engineering at Doosan GridTech. Couldn't ask for a better panel. Since there may be people here who don't know either of you, I thought we'd do some quick 1-minute introductions. Colleen, could you do a quick introduction?
Sure. Thanks, Dan, and it's great to be here with you and Nate. So first of all, I just wanted to say I'm really excited to be here. I've been with Fluence since really its beginning in 2018, and before that with AES Energy Storage, one of the companies that went into the formation of Fluence. I started in the market applications team, and our main job was opening markets. A lot of times we were the first company to bring energy storage into a new market. And that was a really exciting experience. And then I had the opportunity to move into the digital intelligence team and grow our data science team. Because one of the things that we're seeing with the growth of the industry is that data is one of the key elements that is going to enable storage to provide advanced services to customers. Is now a good time to introduce Fluence very briefly?
Absolutely, please.
Sure. So Fluence is an energy storage technology, software, and services company. We have over 2.4 gigawatts of energy storage, either deployed or contracted across 24 countries or territories. In 2020, we acquired AMS, Advanced Microgrid Systems, which is now called Fluence Digital, which provides an asset optimization and bidding platform for energy storage and other technologies. They actually have over 3.2 gigawatts of assets under optimized bidding control. That's not just storage, it's other wind and solar as well. And then very exciting for me as a data scientist, we have over 280 terabytes of global fleet data that we've collected over 12 years of operations. So we can use that to better understand our systems and operate more efficiently and deliver intelligent software to our customers. So I'm really excited to be here today to talk about that.
It's a lot of data, and in this line of work, data is currency. Nate, if you could do a quick introduction for yourself and Doosan on your side as well, please.
Thanks, Dan. And I'd like to thank the ESA for the opportunity to discuss something I'm really passionate about. Thank you for moderating and Colleen for meeting us here. I'm Nate Diamond. I've focused the past 6+ years on becoming an expert in storage controls and optimization, all at Doosan GridTech. Now I run the software engineering team as we break past the 100 megawatt mark and beyond on individual systems. I'm excited to spend time going deep and figuring out how to help IPPs and system owners make money from stored electrons. The light's beginning to dawn. The industry is realizing that storage is software, and I'm glad that we're getting the chance to talk about it here.
Fantastic. Great. All right. Well, let's dive in. A quick introduction on my end as we transition here. My name is Dan Finn Foley. For the past years, I've been lucky enough to partner with the Energy Storage Association, our good friends and hosts here, putting out information on the U.S. Energy Storage Monitor and globally as part of the GTM research team, and now Wood Mackenzie. So I'm the head of the energy storage group here at Wood Mackenzie right now. And so that takes me back to 5 years ago when I first sort of dove into the energy storage market, where storage was doing a lot of things, and there was an opportunity for a lot more value to be recognized. And the market was really then just sort of taking off. And so if we look back 5-10 years, Nate and Colleen, I want to put it to you, how has software been part of that that pathway that's led us to 2021 today, before we start talking about the future?
I
Please
can start off.
dive in, Colleen, please.
Sure. So 100% completely integral to being able to have storage do what it needs to do on the grid. Software and controls are, they cannot be separated from the hardware. And so it's hard to understate their importance. So that these are the fundamental table stakes of providing an operating system to our customers who operate storage. What I can talk about from Fluence's perspective is that, 12 plus years ago, when our controls team started to design the architecture to enable this software, they built in a hierarchical control system so that it made it, I'm not going to say simple because it's definitely not simple, but it made it straightforward to scale from 1 megawatt to 100 megawatts and beyond. So this year we're delivering several mega projects in California that are over 100, or that are 100 megawatts, 400 megawatt hour systems. I should say that include 200 megawatt, 400 megawatt hour systems. And it enables these to operate on the grid. And I'll also say that it's also about working with the market. So understanding what the market need is for the application for storage is critical. We've delivered over 40 different applications for storage. That is, what is it that you need the controls to do on the grid in 29 different markets. So this is, do you need frequency regulation? Do you need primary control response? Do you need 150 millisecond response times, peak reduction, smoothing renewables? So these are all applications that are going to change a little bit, determined by specific market and use case conditions, and controls enable all of that.
Absolutely. Nate, your thoughts sort of on how the evolution of the past 10 years has brought software to the forefront?
Yeah, when I got started in this industry, we were just kind of on the forefront of figuring out even how to control these battery systems. You had PCSs and BMSs, they could make batteries charge and discharge, but when it came to figuring out how you should, as opposed to how you can, that's the evolution that the industry has followed over the past decade. But storage without software is kind of like an engine without a timing belt. It may seem very lightweight relative to the whole thing, but you don't want to get caught with that one. And what we found is no hardware is going to be general enough to solve all of the problems that the industry faces, and to meet a lot of those problems head on. So what software really brings to the table is flexibility. And one of the ways that we found of doing it is very much to Colleen's point, is kind of modeling the industry as a bit of a like 4-tiered pipeline, where on one side there's the market forces, then there's market integration, and then there's the smart controls. This is where you may get into the fast frequency response, integrate, power factor control, integrating with the solar forecast, and then there's the device and hardware level, and each of those is critical. But what you'll find is that on either end, the market side and the hardware side is where you find the least flexibility. And so the software sitting in the middle is what glues those things together. It's what takes a generic piece of hardware and turns it into a tool that can be used to solve problems in the market.
So if you've seen a panel of mine before, you know that I like to talk about where we've been, where we are, where we're going as a general framework here. Highly predictable, just like hopefully energy storage should be with the right software as well. In this case, we've led right into the sort of where we are now, that storage is enabling these things to do that. And we have a lot of storage on the grid right now, but even more importantly, if you follow the Wood Mackenzie forecast, we're seeing exponential growth just this year in 2021 in terms of how much energy storage is going to come onto the grid here in the US. How is storage enabling that? What is the software layer that is enabling that exponential growth today? And then we'll talk about the sort of the tail out to the 5 years as well. Nate, go ahead.
Sure. So there's a couple of things. One is the standardization of communication and modeling with a lot of these different devices. We've got IEEE 2030.5 that is making it so that as new devices are coming on, they have a contract that they have to implement that says how they can integrate at each of these different points. Software is what is going to enable us to very flexibly integrate more and more devices at different levels. As we get into the realm of electric vehicles that are going to be connected throughout the grid, distributed solar adoption increasing very highly, we're going to come to scenarios where the problem of figuring out what to do with all of it as one big mathematical problem is pretty soon going to be intractable. It's just going to be too large. And so this is where flexible software can come in order to balance the needs of all of the different entities in this system, where you can have software that is tailored to maybe managing your storage system at your house versus managing your storage system at your car, when you have it plugged into an electric charger at work, versus an industrial or a utility scale storage system. All of those in the end, they connect together through the grid, and they have to be able to coexist and cooperate together. And that's where software is going to come in, and is absolutely necessary to making that problem even remotely tractable.
Fantastic. I've had a delivery of a piece of artwork apparently by a 4-year-old while you've been talking, Nate. I'll try to, maybe I'll tweet a picture of it. It's energy storage themed, I'm sure. Colleen, this ties into the word that came up during your first comments about where we've been, which is scale, and how that sort of factors in. How is software influencing scale, and how is scale influencing software? What do you think?
Yeah, first of all, 100% agree with Nate's comments. So scale. This actually ties in with what Nate was talking about, and what we've seen in what storage customers and solar and storage customers need in more advanced markets, and markets where there's a wholesale market that you can participate in, is something that enables you to make intelligent decisions about how to dispatch your system. And no longer can kind of an individual human make these decisions the way that traders could do for traditional assets on the grid that are made kind of, well, there are much fewer decisions. So, trading for maybe a gas plant or another type of thermal asset would be done using spreadsheets and experience of the traders. Now there are hundreds of thousands of decision variables that need to be solved every 5 minutes in some markets where the settlement is that frequent, and humans can no longer do that calculation. Even using your intuition, you're not going to do as well as an automated bidding engine platform. So that's what through AMS, Fluence Digital, we're able to offer our customers. It enables more efficient market operations, whether it's storage, solar plus storage, or even a mix of technologies, a fleet of technologies. And then I also just wanted to mention how timely this is with Biden's announcement that we're going to reduce our emissions by 50% by 2030. That's going to require some quantification of the cost of carbon, and that only adds more decision variables for you to solve on. So that's another reason to have that intelligent software layer to optimize how the grid performs to reduce carbon emissions.
Absolutely. Yeah, all of these different layers adding together. And I feel like all of us on the panel agree here about how important software is and the relationship moving forward. But you're both agreeing way too much, so I have to be the contrarian one here. Because if you talk to people who are sort of adjacent to the industry, and maybe some people here who are learning about energy storage for the first time, it seems very simple on its face. An energy storage system is a battery. It is either charging, discharging, or sitting there doing nothing. That's only 3 different things that it could possibly be doing. So how does a system that can only do 3 things become so complicated that you have these dozens or hundreds of input parameters that you're talking about, Colleen?
Yeah. So I could kind of get into like what all of the decision variables are. storage is a unique asset in that you have a reservoir of energy in addition to your power capacity that you can provide. So that essentially frames your optimization in a way that is fundamentally different from, say, a gas peaker. So your hundreds of thousands of decision variables come because you're actually looking out. You need to be able to forecast what you expect prices to be, which also depends on what you expect load to be, what you expect the weather to be out 24, 48 hours. So you start multiplying that, and exponentially you end up with more variables to solve for. So that's why you need machine learning to forecast weather, to forecast prices, and you need a robust kind of optimization platform for that.
Any additional thoughts on that?
Sure. I think that while it may be simple, if it's really just a 4-quadrant pie and you're really just kind of picking a vector along this quadrant, it's like that's not super complex. But the bigger question is not how to do a thing. It's when and why should you do one thing versus another thing. When in engineering we talk about different levels of what you're describing what to do, and the kind of second level is describing to someone why you're doing it, but the third level, the more advanced level, is describing why not do it another way. And so when we're talking about balancing a ton of different needs across the different use cases for different IPPs, utilities, each of them are going to have their own needs for the system. Some of them are going to want to maximize the lifetime of the system. They just want it to be as reliable as they can for as long as they can. Maybe they're trying to maximize the value of their municipal investment into it. Others are looking to simply maximize their returns. They're trying to maximize their IRR from the system. And so one of the things that that software can do when designing a lot of these optimization problems is to figure out those different ways that you may tweak how you decide why and when to do what you want, and capture them into what I call hyperparameters that are kind of like levers that allow you to get a bit of kind of more finer grained control and tune how the system acts. One of them that I like is this notion of aggressiveness. How hard do I push the system in order to eke out that little bit of extra revenue if it costs some amount of health degradation on the back end in order to make that happen? You can imagine how much wear and tear do I put on my car to rush to get to that, to that site an hour away to get an arbitrage deal. And so hardware, even if it can do those simple analyses and solve those simple problems, it's not going to be able to by itself look at that long term and choose the best thing for the system as a whole for the particular customer.
Yeah, let's get into this question of balancing that you talk about, this maximizing revenue. Quick reminder for our audience, please do ask questions through the Q&A box. I'll try to get to as many of them as we can during the discussion. I'm sure you're loaded with questions, type them in now. But this balancing and maximizing question is something that I really want to dive into because Colleen, it gets back into your comment about, these are decisions that don't happen in the spreadsheet anymore. Where if you're looking at a battery saying, oh, for an hour I could provide frequency regulation, I could earn $200 more, but it does this degradation. That's probably not something you can decide on a 5-minute or even faster basis. So Colleen, how does software actually balance that? I know you mentioned machine learning before. There's probably a lot of answers to this question.
Definitely. And it really takes a comprehensive understanding of the technology and the application you're trying to do. So what we talk about internally is the concept of operational cost of your decisions. And what that is when you have the option to dispatch in a certain way and you know that your revenues, or at least you have expected revenues from each decision you could take, there's also going to be an associated amount of degradation that has an associated cost and an associated amount of auxiliary load. Your system's going to get hotter if you do one cycle back to back versus 2 cycles spread out, or 1 cycle at half C rate or your full C rate. So these are all decisions that impact not only how much revenue you can get from the market, but also how much it's going to cost you. And so that's why, we can bring all of those pieces together because we have both that operational understanding as well as the market understanding. So when you pair them together, you get this really powerful tool that enables the customer to understand how this like here and now decision about revenue, the seemingly just about revenue, is influenced by and also impacts their long-term costs of ownership.
Yeah, Nate, this leads into a question from the audience, which is about the duality of that. How will software-controlled energy storage asset management how will their behavior be different if you do it for profit compared to longevity? So revenue versus cost or longevity for a project. But from what Colleen said, it sounds like you really can't pull those two pieces apart.
I would say that you can't pull those two pieces apart, but you can capture that balance and then let what we would call like a meta optimization or an optimization that runs on optimizing those hyperparameters decide what is the best thing to do for this particular system. The other part of this is that it's very difficult to predict when we're talking about a lot of this market volatility, just changes in the market, different unpredictable things on how the systems are going to react and how they may degrade at different rates. You can't predict that really well ahead of time, and it's not necessarily profitable from a system integration standpoint to put tens and hundreds of thousands of dollars in perfectly optimizing those things with all of the uncertainty that you have. And so one of the answers to this that we have found and built into our products is to attempt to, as accurately as possible, model the underlying system inside of the control algorithm, which means designing an optimization that can run when you're talking about the 150 millisecond, fast frequency response and ancillary services markets, that can run a full accurate model of all of the losses and internal state of the system at that speed. And then taking that and designing it in a way that is containerizable and portable so that you can replicate your exact control algorithms as accurately as possible inside of your analysis engine that is deciding, like after the fact, how can I tune, now that I have a month more of data to look at, how could I have done better? How can I do better for tomorrow as you're running the system? And so this is, in the past, many of our analyses were done kind of ad hoc to an extent. It was like a dedicated analyst or engineer gathering all of the data and breaking it down and doing these analyses to, take a dedicated experience, sometimes doctorate level and analysts for weeks at a time to put these analyses together. But by taking our algorithms and building it into an engine that uses those exact algorithms in order to, like literally the same software in order to model how the system will react under different conditions, we can automate a lot of those analyses. We can figure out we can do automated sensitivity and volatility analyses, and then we can also optimize those hyperparameters after we've already deployed the system. We can tune them to eke out that couple of percentage points of performance and say, back to the original question, when is it worthwhile, not necessarily relative to maximizing revenue, but maximizing IRR, when you're talking about maximizing money now versus money 10 years from now, or for some of these things, 25 years from now, or when you're trying to do things like determine if you have a 25-year-long DC coupled, let's say, storage system, and you then are going to be doing augmentations, as we call them, in order to increment and add the number of storage units in order to compensate for loss of state of health of the base system. If you can minimize the number of those by making your system last a little bit longer, all of that needs to get plugged into that IRR calculation to say, this is the best decision that we can make right now for tomorrow to make sure that we're making the best money, the most amount of money.
Great. We had a question come in from the audience that I love, which is about the consolidation of the market. There's been a selling spree, buying spree for the past couple of years about software solutions and the sort of visibility. Colleen, of course, mentioned Fluence's acquisition of AMS, for instance. What is the software landscape really looking like in terms of, is there room for is there an advantage to having software that's integrated within a broader business model? Is there room for sort of a third-party layer on top of that? Which I guess sort of ties into our question about differentiation. if hardware is increasingly commoditized, how does software differentiate? So yeah, I'd open it to the floor there. Who wants to tackle that? You could talk about it for an hour, I'm sure, but Colleen?
I'll try to offer some brief thoughts on that. It's a great question. So one thing that we've learned is that software has to be flexible to accommodate different technologies. And while we continue to evolve and develop our software and controls platform, the fundamental architecture of the controls platform has basically stayed the same as our hardware platform has evolved. So we're now on our 6th generation GridStack and SunStack, our DC coupled solar plus storage solution. And our fundamental control software has evolved to, has been flexible enough to accommodate each of those different technology platforms. And a further point just about that is it also allows us to potentially integrate other technologies. So if there's another storage technology that begins to compete economically with lithium ion, that can be incorporated into the same basic control system. And on the other hand, I think getting back to that question, which of the third-party platform, that's a really good tie-in with what happened with AMS coming on board. So there, we may have software that, or I should say, we developed this base layer of software that that we can apply to a wide variety of applications in a wide variety of markets. But you can kind of think of our systems like an iPhone. So it's great hardware, it's reliable. We bring it with a core set of applications that we know are applicable to almost every user, or you can select applications for your particular need, but you can also add to it with an app if a third party makes something that's useful for you. So to that point, yes, the software is really layerable. It's something that we are able to do with AMS. It doesn't necessarily have to be part of the Fluence system to do that. I think that's the forward-looking vision of the future.
So I think that there's a lot of value in what you said there. I think in the end, a lot of the opportunities are going to come in terms of reducing cost, as well as making the problems that we're modeling a bit easier to solve relative to a lot of these different integration points that we've talked about. One of the big costs that a lot of even developers don't necessarily consider fully when they're choosing which system to go with is this notion of how the software pairs with the hardware, right? It turns out that that is a huge portion of the cost of integrating new technology is a large portion of the cost, even if you design your system to be design your system to be as flexible as possible. There's still going to be those integration points, and as much as you can minimize those and minimize that cost, that is where you're going to get a lot of these big jumps in cost savings. You can imagine this notion of the light bulb, that there's this standardization component and then there's this innovation component on top. And so as much as you can standardize it, you can realize a lot of these gains. And so there's a couple of different approaches that different companies have taken, and some of them are looking to make the hardware as homogeneous as possible. If they can make, a modular battery storage unit with PCS and it's just packaged together, then that solves a lot of that problem. They know how it's going to act, and scaling it becomes easier in that sense. But you may lose out on some of that flexibility, or you need to have enough different standardized modules to be able to handle a lot of these different cases. But that also limits you, it kind of locks you into one technology potentially. If you could imagine buying, whole hog into CFLs, right? Versus another methodology would be to design that standard integration point, for instance, by standardizing the device communication, to say, if there were a third party that came in and said, we have a gateway, and that gateway turns any of these arbitrary devices into a standard communications point. Companies could do that themselves, but if you get to the point where you have the best control software, and that is one of your major costs, and somebody else can come in and say, I can reduce that cost of integrating that new liquid cooled battery, that new vanadium redox flow battery for you. That is where we're going to get a lot of these innovations in that third parties can absolutely capitalize on.
Yeah, that's great. This ties into a question that's being asked broadly in terms of, software doesn't come for free, right? This is an element that's being layered on and it's adding value. So the idea is that it's making its money back. But how does that factor in when it comes to things like risk, when it comes to things like uncertainty? If software sort of has a cost associated with it, how does it then make up that cost in terms of what are the uncertainties that you really reduce here? Is it merchant risk? Is it battery degradation? What are you really firing back on?
There's quite a few different things that you can be balancing against. I think one of the biggest risks going into when you're designing, gigawatt scale plants is if you're planning out 25 years with a lot of these augmentations coming in, then you're kind of planning on what the market is going to be like for even lithium ion 7 years out, right? And so when you're choosing a software stack, even if now it seems like they've solved the problem of being able to standardize and just plan out that roadmap for how you can grow the site, there's a ton of risk in there. And so going with solutions that are taking what I would call flexibility in depth, like trying to build flexibility as a first-class citizen into all parts of their software, that is where going with a particular software stack makes it a lot easier to be flexible later on when you've put in, hundreds of millions, billions of dollars into these different sites. And so that's where this is, again, where software is going to be one of those differentiators, that those changing market conditions can be handled without significantly having to re-architect and redeploy an entire site.
Colleen, go ahead.
Yeah, I would just add, definitely agree. There was a great post, but I actually forget where it came from, on the changing market applications in the UK in the last 3 or 4 years. And it was just a pie chart of the last 3 or 4 years of where storage assets were getting their revenues from. And essentially it changes in name and significant application every year. And that's exactly why flexibility built into software is so critical. And then I would just add on the question of kind of how do you balance that risk and uncertainty? It really does come back to making sure you're taking into account both your operational costs and your revenue potential throughout the system. And that the way that you balance that is through the risk preferences of the customer or the asset operator. So a choice of either how risk averse or how risk tolerant are you, but also just what is your internal discount rate, and how much are you interested in, which essentially allows them to translate that into how much do you want to use your system now versus save for later.
Do you mind if I comment on that? There's one other thing relative to that managing risk, is that there's a lot of interesting licensing agreements that the software industry is kind of looking towards in order to allow IPPs that view these energy storage systems as financial vehicles, right? In order to hedge that risk, where you're doing some kind of risk sharing agreement with the integrators and with those that are managing and doing the bidding and optimization. And this can be mutually beneficial because it also then can incentivize the integrators and the optimizers to do better, because if they increase the performance of the system, then if they get a cut of that, then as the market changes, they're incentivized in order to, there's a built-in function for them to handle that flexibility. It directly incentivizes that level of flexibility. And so when we're getting into these, especially I would say the market integrated systems, as opposed to the systems that maybe are focusing in on PPAs for a much more steady, lower risk revenue profile, looking into those profit sharing schemes can be incredibly, it can build in a lot of resilience into that kind of agreement, that can handle these changes in market conditions.
Great. We've had a couple questions come in that talk about this risk, and it's pushing the question more into the future here, which is about, I'll frame it this way, about the more of a distributed energy environment. There's a question here about what's the role of edge computing in a high DER EV environment? What are the possibilities for tokenizing energy in a decentralized model? And I'll sort of wrap that around two key questions here. Who is controlling the storage? Who's dispatching it? And what is the future of aggregation, and how does software play a role there? Again, that can be a whole other panel. So try to summarize that really quickly. Colleen, what do you think?
Sure. Yeah, it could definitely be a whole other panel, but I'll just answer briefly. So whether you're talking about aggregating a fleet of systems or a fleet of distributed systems, or an array of what we call our cubes at a site, you're essentially able to use the same underlying software principles. The underlying control principles remain very similar. And whether you're if you're optimizing kind of a fleet of systems or a single solar plus storage asset, the kind of underlying optimization, if you're operating in a market, or if you have a PPA that you have to deliver a certain amount of fixed capacity for, or if you have a mix of the two, which we're actually probably going to see a lot more of in California and maybe in Virginia, as Virginia is growing a lot in their energy storage area. It's underlying the same principles. So that's the point I wanted to make, is just having flexibility in your software controls and your intelligence software is key.
Flexibility. Nate, what do you think?
So as we get into even the hint of possibility of something like transactional energy, I think that one of the key kind of guiding visions within our software stack is the notion of smart control where you need it, which is to say that we've already had projects that are integrating with vanadium redox flow batteries and EVs. And as we're looking to the future, one of those big questions is, how do you balance, especially for an asset that you don't necessarily own, but you have some control over, such as these EV systems? How do you balance all of those different, that multi-objective optimization, all of those different needs from each of the different participants? And so in the end, a question may not necessarily, the question may need to be more generalized and not just who is doing the controlling, but how much control does each level get, and how much control does each level want? I think a great example of this is if we have an aggregated, you can imagine the concept of a parking garage that installs a ton of V2G charging stations throughout and turns the parking garage into a stochastically available battery storage system where everybody parks in and they connect throughout the day. If I were to come in and connect my car into that parking garage, the amount of control that I would probably, the minimum amount of control that I would require, aside from minimizing my cost of charging at the parking garage, is making sure I have enough energy in my car to get home. That's going to be my minimum bar, right? But I'm also going to need some flexibility to say, if I'm leaving work and then I'm going to go immediately take a road trip, I'm going to want to be able to have my EV be at 100% before I hit the road at 6 o'clock. So we're going to need some notion of control at all levels of this hierarchy. And that's why we're going to need software that is flexible, not just in the modeling of the underlying systems, but also in the ways that you are able to add in those objectives and add in those constraints and inputs into it to be able to solve the problems of everyone. Because otherwise, I may know that charger is there. I'm not going to give them full control of my battery if I'm not confident that I'm not going to get, I'm not going to have to turn off my AC to have enough juice to get home in the middle of the sweltering Texas heat, right? So I think that we're going to need smart control where you need it throughout that stack.
Yeah, again, the smart control, adding in this human layer of complexity. Let me throw it even further in the future to another layer of complexity on non-lithium technologies, long duration storage. When it comes to software and being flexible, how is that flexibility being ensured for the technologies that are going to emerge into commercialization 5, 10, 15 years from now?
So one of the things
Yeah, Nate, go ahead.
one of the things that we've been doing for this is when we are design relative to that kind of that flexibility in depth. A great example of this that I've come across personally is we had an opportunity to engage in a project in which we needed to radically change the underlying optimization in order to model a new type of system. And because of the to throw out a couple of software architecture design terms like solid design and designing around these contracts and building in this flexibility into the system, a small team, just 4 of us, were able to completely replace the underlying optimization that was designed at AC controlled standard lithium batteries to be able to support this radically different software control architecture in about 6 weeks. It is the key thing here is that you have to challenge your assumptions about what is going to be static and what's going to be dynamic. And the best way to do that is to think in terms of standardizing communication contracts in between these different components so that it's very easy to swap out one internal component and have a drastic change in the behavior of the system without incurring huge, costs throughout the entire, not having to re-architecture the entire thing.
Fantastic. Colleen, what do you think? Are there additional pitfalls in there that make this tricky, that software has to come in and smooth over when it comes to new technologies?
Well, I have no doubt there will be tricky things that need to be figured out as you start integrating some of these new technologies. But I'll just go back to the designing our controls and software with technology agnosticism at the core. So you can start with lithium ion technology, and if flow batteries come in for an application that makes sense in the future, you could start integrating that as well. And you could imagine a kind of hybrid system where you not only have DC coupled solar plus storage, but you also have kind of a long duration storage aspect of that, whether it's thermal or flow or whatever, what have you. And that could be, designed, the controls and software designed along the same principles. But the interesting thing that you would have there is you would have to start thinking about a much longer time horizon for optimization.
Right. Yeah, that longer time horizon is going to be fascinating. And speaking of long time, I wish we could have this conversation for a much longer time, but we are running up on the end of our 45 minutes here. So I wanted to pause and ask our panelists one last question, which I usually try to ask. I used to call it the water cooler question, but now I guess it's kind of the kitchen sink question, where if you have an attendee who's looking at this storage panel saying storage is software, and they're off having a Zoom meeting with their colleagues later in the day, what is the key 1-minute takeaway that person can take when their colleagues, or maybe their boss who's wondering why they just spent some of their day at this conference, what is the key takeaway on how software and storage are interacting right now and why it's important moving forward? Nate, let me start with you.
So we found that when we're designing our software, that the amount of time spent thinking ahead and designing for generality saves orders of magnitude of time later. That the more work and thinking that you do now into how that system can change it's the difference between a senior engineer and a junior engineer. It really is about maturity in your software design. And so spending an hour listening to this conversation could be the sparking point to a vast different a paradigm shift in a particular approach that a given company is going to take that could save them, no joke, millions of dollars down the road, even just doing a little bit of extra planning now. And so it's absolutely worthwhile to do this extra planning and have these discussions now instead of when you're at the point of building the plant or even after you've already built it.
Stitch in time saves 9, I think is the idiom, if I'm using that correctly. Colleen, last closing thoughts here.
Yeah, I mean, I think we'll end on violent agreement. Basically, the planning aspect is critical, and we've built our systems so that we built our software controls and our intelligent systems so that the same components that are used to make decisions about your day-to-day or minute-to-minute operations can be used to help you model your decision making for before you buy an asset. So before you build your storage, you need to have a plan for what is your investment plan for the next 20 years, and what do you want this asset to do. So in order to do that and do it well, you need to be modeling the same things that you're using to modeling those those minute-to-minute decisions, whether that's making sure you have a good thermodynamic model of your storage system, a good controls model, understanding of degradation, optimization of your system, optimization of revenue decisions. Those principles are fluent throughout the entire lifetime of the system.
Fluence throughout the entire lifetime of the system. Yep. Fantastic. Nate Diamond, Dr. Colleen Leakin, thank you so much for joining me today. Thank you so much for the Energy Storage Association for hosting this. We didn't get to all of your questions. I think people will be going to the lounge after this to hopefully keep the conversation going. Bring your questions up there. My key takeaway will be from my 4-year-old from the art piece that we have here. It appears to be sort of a complex element. I feel like there's some aggregation questions in here, really bringing home the fact that there is some complexity around storage. So I'd like to thank Arthur for his input into the conversation as well. Thanks so much, everybody. Looking forward to keeping this conversation going. And thanks again to our panelists.
Thank you.
Thank you so much.